Hello, this is Sareen from Exam Help Lab. Today I'll be solving Cambridge International AS and E-Level Chemistry, Paper 2, AS Level Structured Questions, 9701, Paper 2, Variant 2, February-March 2020. Question number 1. Group 2 metals form alkaline solutions in water. A. Part 1. Write the equation for the reaction of calcium oxide with water. So a group 2 metal like calcium, when reacts with water, it forms calcium oxide, and which is alkaline in nature. When that same metal oxide reacts with the water, the solution forms as metal hydroxide. So calcium oxide, when reacts with water, it forms metal hydroxide, which is calcium hydroxide. Part 2. Identify the ion that causes an aqueous solution to be alkaline. So an alkaline solution has more of hydroxide ions than it has hydrogen H plus ions. So these ions are hydroxide ions. Part B. The table shows the melting points of some group 2 metal oxides. Explain the trend in the melting points of the oxides down group 2. So the melting point seems to decrease down group 2 due to weaker forces of attraction. Here the oxide ion size, which is O2 minus ion, it remains the same, but from Mg2 plus to barium 2 plus, the cation size increases, which causes this force of attraction between the cations and the oxide anion to get weaker. So the two factors which cause this decrease in melting points down group 2 is that weaker force of attraction between the cation Mg2 plus, calcium 2 plus, and barium 2 plus, and the anion, which is oxide ion. And this force of attraction gets weaker due to the increase in the size of the cation from when we go down group 2. So cation size increases. Part C. Oxygen reacts readily with some metals, but each group 2 metal requires a strong heating to start the reaction with oxygen. Suggest why strong heating is required to start these reactions. So before the reaction proceeds, there is some amount of energy required to start up the reaction, and that energy is called the activation energy. So to overcome that high activation energy, we need some prior heating. So we can write that to overcome high activation energy. But the beryllium oxide reacts with hydrochloric acid to form molecules of beryllium chloride to reduce the bond angle in beryllium chloride. So beryllium has two outermost electrons, with each being shared with a single chloride ion. So one is being shared with this chloride ion while the other one is being shared with the other chloride ion on the left. So the repulsion is going to be just due to these two paired electrons of beryllium. Thus the bond angle would be of 180 degrees. Just like that of carbon dioxide, where after all the bondings have been done, there is no electron left of carbon atom, which is unpaired. Part E. Unlike the other oxides of group 2 metals, beryllium oxide is amphoteric. Give the meaning of the term amphoteric. So amphoteric oxides are oxides that react with both acid and alkali. Part 2. Beryllium oxide and aluminium oxide have similar chemical properties. The beryllium hydroxide ion is a product of the reaction between beryllium oxide and excess concentrated hydroxide ion. Construct an equation for this reaction. So beryllium oxide and aluminium oxide, they have got similar chemical properties, which means that beryllium oxide can also react with H plus and OH minus. So just like aluminium oxide with sodium hydroxide would give sodium aluminate, which is NaAlO2 and water, beryllium oxide with NaOH, means OH minus ions, can also give us this anion. And to balance our number of hydrogen and oxygen, we can add H2O to the left And we will balance our equation with adding 2 to this side. Part F, magnesium oxide reacts reversibly with chlorine according to the following equation. Under certain conditions, a dynamic equilibrium is established. Part 1, state 2 features of a reaction that is in dynamic equilibrium. In total, there are 3 to 4 features of a dynamic equilibrium in your chemistry AS level and A level syllabus, which you need to have memorized for your external examinations. So one of the features is that the rates of both forward and backward reaction is equal. And the second one is that it occurs in a closed system. Part 2, the equilibrium constant Kp is given by the following expression. At 10 to the power 5 pascals and 500 kelvins, only 70% of the initial amount of chlorine gas has reacted. Calculate Kp and state its units. So the equation is that 2 moles of chlorine gas, and you must know that we do not consider anything other than gases in this equilibrium constant formula. So we're just going to consider chlorine on the left and oxygen on the right. So 2 moles of chlorine produces 1 mole of oxygen gas. So initially, we suppose that chlorine had X moles reacting, and while the equilibrium was not established, there were 0 moles of oxygen that had formed. And the question states that only 70% of that chlorine gas could react, meaning that the 30% of the chlorine gas will remain as it is in equilibrium. So at equilibrium, 0.3 of total number of moles of chlorine that were at equilibrium. And that 70% whole doesn't change to oxygen, since the mole ratio of chlorine to oxygen is 2:1. So again, half of that 70% changes to oxygen, and half of 70% is 35% of total chlorine molecules. So 35% of total X is going to be 0.35X. So when equilibrium was established, there were 0.3x moles of chlorine and 0.35x of oxygen, where x is the number of moles of chlorine initially before establishing the equilibrium. So now the mole fraction is in the fraction of 6/13, and of oxygen is 7/13. The Kb has a formula that partial pressure of oxygen, which is the total pressure of the system multiplied by its mole ratio, which is 7/13, divided by partial pressure of chlorine, and that should be squared since we're using 2 moles of chlorine in the equation. So this will also be multiplied by its mole ratio, that is 6/13, and this will be squared. And you will have a Kp of an equilibrium constant of 2.53 into 10 to the power of -5, and this wasn't pascals and this was Pascal square, so the units will now be per Pascal. Question number G, magnesium peroxide is made in the following reaction. The peroxide ion is O2 with the total power of 2 minus. Deduce the average oxidation number of oxygen in the peroxide ion. So there, in the peroxide ion, there are 2 atoms of oxygen with a combined charge of -2. So each oxygen will have an oxidation number of -1. But to determine the term enthalpy change of formation, so this is the enthalpy change when 1 mole of a substance forms from its elements in their standard states. Part 3, use the data given to calculate the enthalpy change of formation of MgO2. So using the previous equation, which is in the part 1, that MgO reacts with H2O2, that gives MgO2 plus water. The enthalpy for this reaction was -96. and we are supposed to find the enthalpy change of formation of MgO2. Means we will have a magnesium in its standard state and oxygen in its standard state to form MgO2, and this is what we have to calculate. Alongside, we are also given with the enthalpy change of formation for MgO, H2O2, and H2O. So for the enthalpy change of MgO, we needed MgO plus O2. For H2O2, we needed H2 in its standard state plus oxygen in its standard state to form H2O2. And for H2O, we need hydrogen and oxygen in their standard states. Now we are also supposed to balance all these three parts. There is just 1 mole of Mg on all three sides, and there are 3 moles of oxygen. So I'll add 3 by 2 over here, and 2 moles of hydrogen. Okay, that's balanced now. Now I'll start labeling these arrows with their respective values. So formation of MgO is negative 602 for 1 mole of MgO. For H2O2, it's negative 188. For the formation of 1 mole of H2O, it's negative 286. And we are to find this value. Our direct route of enthalpy is this one, while this is the indirect route. The direct route is reaching the substance right from their elements, and the indirect one is to convert these elements into first these two substances and then to the final product. So our direct route is of x plus minus 286. Our enthalpy for the direct route is going to be equal to the enthalpy for the indirect route, and that is the rule. So negative 188, negative 602, negative 96. And that's how you get a value of x as negative 600 kilojoules per mole. And this is the enthalpy change of formation of MgO2 from its elements in their standard state. Part 4. Magnesium peroxide decomposes slowly to form magnesium oxide and oxygen. Use your answer to G part 3 and the data in the table to calculate the enthalpy change of this reaction. So magnesium peroxide changes to magnesium oxide plus half of oxygen. This is unknown to us. Now we can use the values from the above chart to get the value for x. So to form MgO2, we need Mg in its standard state plus oxygen in its standard state, and the same goes for MgO. So the enthalpy change of formation of MgO2 is what we calculated in the previous part, that is negative 600. So negative 600 is for 1 mole. And the enthalpy change of formation of magnesium oxide of 1 mole is negative 602. So negative 602. Our direct route to reach MgO plus oxygen is negative 602, and the indirect one is x, negative 600, and you get a value of enthalpy change of this reaction as negative 2 kilojoules per mole. Question number 2, part A. The group 17 elements, chlorine, bromine, and iodine, are nonmetals that show trends in their physical and chemical properties. Describe the trend in the color of the group 17 elements down the group. So the colors, they get darker as we go down the group. So we can write that halogens get darker as we go down the group. Part B, the group 17 elements can oxidize many metals to form halides. Part 1, describe the relative reactivity of the elements in group 17 as oxidizing agents. So the elements which are on the top, they are better at oxidizing, while the ones that are at the bottom of the group 17, they are better at reducing elements. So I can say that the oxidizing agents get weaker down the group, because as we go down the group, they start to lose their oxidizing power and they start gaining their reducing power. So iodine as compared to chlorine will have more reducing power than oxidizing, and chlorine is a better oxidizing agent than iodine. Part 2, chlorine reacts with hot tin metal to form tin 4 chloride. Tin 4 chloride is a colorless liquid at room temperature, so it is in the liquid state at room temperature that reacts vigorously with water to form an acidic solution. So does the type of structure and bonding shown by tin chloride explain your answer? So tin chloride has covalent bonding, and that's why it hydrolyzes into water. Otherwise, those that have ionic bonding with a lattice structure, they will only dissolve into water because of their strong bonding. So I can write that tin chloride has covalent bonding because it hydrolyzes into water. And as far as their structure is concerned, it has a simple molecular structure because it has a lower melting point, as it is stated right here that tin chloride exists as liquid at room temperature. So tin chloride has simple molecular structure. Because it has low melting point. Part C, the group 17 elements form soluble halides with sodium. Part 1, describe what is seen when dilute silver nitrate is added to sodium bromide followed by aqueous ammonia. So these are the halide tests which you need to remember for chloride ion, bromide ion, and iodide ion with silver nitrate, aqueous ammonia, and concentrated ammonia. So upon addition of silver nitrate solution to the bromide ion, a cream precipitate forms. Which is partially soluble in aqueous ammonia. Part 2, sodium chloride reacts with concentrated sulfuric acid to form hydrochloric acid and sodium hydrogen sulfate. Explain the difference between the reactions of concentrated sulfuric acid with sodium chloride and with sodium iodide. Your answer should refer to the role of the sulfuric acid in each reaction. So when NaCl reacts with sulfuric acid, it forms HCl plus NaHSO4, and the reaction stops right there. While when NaI reacts with H2SO4, it forms Hi plus NaHSO4, and the reaction doesn't stop there. In fact, the Hi will get further oxidized by H2SO4 and will form various products including iodine gas. So we can write that HCl can't be oxidized by H2SO4 as chloride ion is much stronger in oxidizing than H2SO4. But Hi oxidizes to iodine gas when H2SO4 is added. Because iodide ion is a better reducing agent. It will get oxidized and will bring reduction to another substance. Part D, the hydrogen halides are useful reagents in organic and inorganic reactions. Part 1, describe and explain the trend and the boiling points of hydrogen halides, HCl, HBr, and Hi. So the boiling points down the group increase due to more number of electrons, which strengthen their van der Waals forces, which is the intermolecular forces between the between HCl, HBr, and HI. To describe and explain the trend in the thermal stabilities of the hydrogen halides HCl, HBr, and HI. So the stability, it decreases down the group. And the reason to that is because of greater bond length that leads to reduced bond energy. So the more the distance between the nuclei of each ion, the greater the bond length is, and as a result, the bond energy, which is the energy required to break that bond, it reduces. Part E, Lucas reagent is a mixture of HCl and zinc chloride. Primary, secondary, and tertiary alcohols can be distinguished by the reaction with Lucas reagent. Alcohols react with the hydrochloric acid and Lucas reagent to form halogenoalkanes. Zinc chloride acts as a homogeneous catalyst for these reactions. Part 1, explain the meaning of term homogeneous. So homogeneous catalyst is when the catalyst is in the same phase as of reactants and products. Part 2, pentane 3O reacts slowly with HCl to form a secondary halogenoalkane. Complete the equation for this reaction using structural formula. So pentane 3O reacts with HCl, OH gets replaced by the chloride ion, and the side product will be water. So C2H5, CHCl, C2H5 plus water. Part 3, the fastest reaction shown by Lucas reagent is with a tertiary alcohol. Draw the structure of the tertiary alcohol that is an isomer of pentane 3O. So a pentane 3O has 5 carbon atoms with OH on the 3rd carbon atom. A tertiary alcohol will have a central carbon atom with 3 of its sides bonded to alkyl groups, and the 4th side will be bonded to the OH group. So it would be somewhat like this. So an isomer of pentane 3O would be this one. Part 4, tertiary alcohols tend to react with Lucas reagent using the same mechanism as in their reaction with HCl. Suggest the type of reaction shown by tertiary alcohols with Lucas reagent. So when tertiary alcohols, they react with HCl, the Cl substitutes OH functional group. So that is substitution reaction. Question number 3, part A, glycerol is widely used in the food industry and in pharmaceuticals. A series of reactions starting from glycerol is shown. Part 1 suggests the reagents and conditions for reaction 1. So reaction 1 is about change in primary alcohols to COOH, which is the acid groups, and this is the secondary alcohol which changes to a ketone group. And this is all oxidation, so the reagent would be any oxidizing reagent. So I can use acidified chromate ion, and the condition would be heat under reflux. Part 2, name the reaction mechanism for reaction 2. So this is nucleophilic addition reaction because HCN over here acts as a nucleophile and no other side product is released. Nucleophilic addition reaction. In addition reactions, there are no side products. Part 3, give the observation you would make when 2,4-dinitrophenylhydrazine is added to P. So 2,4-dinitrophenylhydrazine gives orange precipitate for carbonyl compounds. P has got a ketone group, so it gives a positive result. You can say that orange precipitate forms. Part 4Q does not show optical isomerism. Explain why. So an optical isomer will have a central carbon atom attached to 4 different atoms or group of atoms. While in Q, there is this central carbon atom attached to 1 CN, 1 OH, but 2 COOH groups. This means that the central carbon atom, we can write that the central carbon atom is not attached to for different group of atoms. Part 5.1Q is heated with excess aqueous ethanoic acid in the presence of a catalytic amount of sulfuric acid. 2 reactions take place to form compound R. So Q has 2 carboxylic acid groups, 1 nitrile group. There is this nitrile group, 2 carboxylic acid groups, and an alcohol group. So when it reacts with ethanoic acid in the presence of sulfuric acid acting as a catalyst, the first is the change of nitrile group to carboxylic acid, which is acid hydrolysis. So one of the reactions that it undergoes is hydrolysis reaction. And the second is from the hydroxyl group to ester linkage, which is COO, and that is esterification. Part B, glycerol can be used as a starting material in the manufacture of nitroglycerin. Nitroglycerin decomposes rapidly on heating to form a mixture of gases. A sample of nitroglycerin decomposes, releasing 1.06 decimeter cube of oxygen at 850 kelvins and 10 to the power 5 pascals. Part 1, calculate the mass of nitroglycerin that composes. So for this, we first need to find the number of moles of oxygen forming. So for any ideal gas, the equation is PV is equals to nRT, where N is the number of moles, and that is equals to pressure multiplied by the volume, and the volume is in decimeter cube, so we must convert that to meter cube, so that it becomes 1.06 into 10 to the power of negative 3 meters cube divided by 8.314, which is a constant value, multiplied by the temperature 850 kelvins. And we find the number of moles of oxygen being formed as 0.015 moles. Now, the mole ratio of nitroglycerin to oxygen is of 4:1, so the number of moles of nitroglycerin is equal to 0.015 into 4, and that is equal to 0.06 moles. Now, to deduce the mass of nitroglycerin, we must multiply its number of moles with its relative formula mass, which is 227, and we get mass of nitroglycerin as 13.62 grams. Part 2, calculate the total volume of gas released by this decomposition at 850 kelvins and 10 to the power 5 pascals. So the total moles of gases forming is 12 plus 10 plus 6 plus 1, which is 29 moles of gases formed. So 29 multiplied by volume of each gas at 850 kelvins and 10 to the power 5 pascals is of 1.06 decimeter cubes, and that gives me a combined volume of gas as 30.74 decimeter cubes. Part C, fats are compounds made from glycerol and unsaturated carboxylic acids. Unsaturated carboxylic acids means this structure has got C to C double bond and a carboxylic acid group. 4-pentanoic acid is an example of an unsaturated carboxylic acid. Part 1, give the molecular formula of 4-pentanoic acid. So there are 1, 2, 3, 4, 5 carbon atoms, 1, 2, 3, 4, 5, 6, 7, and 8 hydrogen atoms, while 2 oxygen atoms. Part 2, draw the repeat unit of the addition polymer that can be formed from 4-pentanoic acid. So an addition polymer forms when this carbon-to-carbon double bond breaks and forms 2 new sigma bonds on these 2 sides. So a repeat unit would look somewhat like this. And you put the bracket around it, right? N stands for the number of repeat chains. Part 3, unsaturated acids are often brominated before being added to soft drinks. Complete the mechanism for the addition of bromine to 4-pentanoic acid. Include the structures of the intermediate, and the product of the reaction include all charges, partial charges, lone pairs, and curly arrows. In the mechanism, R has been used to represent CH2 twice COOH. Now, carbon-to-carbon double bond is high on electron density, which will make this bromine atom partial positively charged, while the other one will have a partial negative charge. The Br to Br bond breaks heterolytically, so this arrow will have its head towards the negatively charged bromine atom, and this positively charged bromine atom will be attracted towards the electron-dense C2C double bond. The intermediate of this reaction will have one of the bromine attached to this carbon atom, while the other carbon atom will have a positive charge, which will be attracted towards the negatively charged bromine with a lone pair of electron. And the final product would be addition of Br atoms. Part D, a reaction of another unsaturated carboxylic acid, T, is shown. Part 1T is one of a pair of geometrical cis-trans isomers. Draw the other geometrical isomer of T and explain why the molecules exhibit this form of isomerism. So we can bring the COOH to this side, and that will give me the other cis-trans isomer. So these two structures, they exhibit cis-trans isomerism because they have got 2 different group of atoms attached to each carbon atom of C2C double bond. This carbon atom is attached to a C6H13 and 1 Br atom, while this carbon atom is attached to 1 carboxylic acid group and a hydrogen atom. So each carbon atom in a C2C double bond is attached to 2 different group of atoms, and that's one property of geometrical isomers. And the other one is that there is a restricted rotation about C2C double bond. So we can write that each carbon atom is attached to 2 different atoms, and there is restricted rotation about C to C double bond. These are the 2 features of geometrical isomers. Part 2, identify the reagent used to convert T to U. So T must have undergone a reaction with hydrogen so that the new product, which is U, will have more hydrogen atoms attached to it. So the reagent was hydrogen gas. Part 3, the C to Br bond has an absorption between 500 centimeters, 500 per centimeters, and 600 per centimeter in an infrared spectrum. The infrared spectra for both T and U have absorptions between 2850 per centimeters and 2950 per centimeters. These correspond to C2H bonds. So identify 2 other absorptions that would be seen in the infrared spectra of both T and U. So over here, when you see T and U, they have both got a COOH, the carboxylic acid group, and they have also got C2O double bond, which has its own separate peak on an infrared spectrum. So we can write that both T and U will have a peak at at 1680 to 1730 per centimeters, due to C2O double bond, and they both have got carboxylic acid groups, so they both will have absorptions at 2500 to 3000 per centimeters due to carboxylic acid group. Now, T will have an exclusive absorption due to C to C double bond, which is not present in U. So for C to C double bond, an absorption will be around 1500 to 1680 per centimeters due to C double bond. So we're done with this paper. Thank you for watching.